Our next presentation is entitled The Evaluation of Vegetation Indices to Assess Yield and Crop Quality Parameters in Peanut. And our presenter is Sara Studstill.
Good morning, everyone, and thank you for that introduction, Dr. Kimmerai. Can you see my screen?
Yes, we can. Looks good.
Okay. As he said, I'm Sara Beth Studstill, and I'm a PhD student under the direction of Dr. Scott Monfort at the University of Georgia. And I will be presenting a section of my PhD work entitled The Evaluation of Vegetative Indices to Assess Yield and Crop Quality Parameters in Peanut. There are close to 300,000 hectares of peanuts grown in Georgia, making it the 6th largest commodity in the state and making Georgia the leading producer in the United States, with approximately 50% of the nation's production. In 2018, the farm gate value totaled over $625 million, and around 75 counties grow peanuts in Georgia, but only 10 of those produce nearly 50% of the state's peanut production. The average peanut yield across the state of Georgia is approximately 4,500 kilograms per hectare. However, the range of yields can be quite large, and buying points could greatly benefit from a method that predicts yield and crop quality before the crop makes it to their facilities. Yield is the ultimate deciding factor in how much a grower makes at the end of the season. However, the grade of the crop can affect the profit of the crop. Grade is determined by the total of sound mature kernels, or TSMK. TSMK is determined by the number of sound mature kernels, or SMK, plus sound splits, known as SS, and then they take away any deducts the grower might face. Sound mature kernels are undamaged whole kernels, while sound splits are undamaged split kernels or broken kernels. One of the first deducts that a grower may face is known as loose shelled kernels, or LSK. This is any undamaged kernels not in the shell. Another of these deducts is foreign material, known as FM. Everything but in-shell peanuts and loose kernels is known as foreign material. This can include dirt, rocks, vines, sticks, even insect parts, and all the holes. Another one of these deducts is other kernels, known as OK. These are any smaller, less mature whole kernels. And damaged kernels, DK, are another deduct. These are any kernels that are deemed inedible. All of these factors together create the grade of the crop, which is a representation of the overall crop quality. Precision ag has become a growing topic in peanut research over recent years. It has proven that aerial imagery, when looking at NDVI and NearInfrared satellite imagery, can predict yield in Australia. Another form of precision agriculture that many farmers across the state of Georgia use is the Peanut RX program. This is a pre-season risk assessment for disease that growers can use to determine a fungicide program ideal for their risk and situation. Prescription maps for weeds and diseases have also been used in peanut research for pesticide applications. This aims to cut down on the amount of pesticides a grower sprays. UAVs have also been used to assess fields for leaf spot and tomato spotted wilt virus. Precision ag has made many great advances in peanut over the years, and it can be helpful in determining yield and crop quality of a crop before it's harvested. With that knowledge, we hypothesize that vegetation indices can be correlated to peanut yield and crop quality parameters associated with grade. Therefore, our objective was to evaluate vegetation indices using red, green, and near-infrared aerial imagery to determine correlations to peanut yield and crop quality parameters. This research took place over 2018 and 2019 in Coffee County, Georgia. And in 2018, we used 3 grower fields. And in 2019, there was a total of 14 growers fields. All fields were planted to the variety Georgia 06G, and we had both dryland and irrigated fields. However, in 2018, all 3 fields were dryland fields. Planting dates ranged greatly throughout the 2-year study, and this meant that aerial imagery was taken somewhere between 85 and 132 days after planting for all of the fields. This research was conducted using a plane-mounted camera because of the large area we were covering, and the plane used was a Cessna 206, and we used a Canon 6D camera that was modified to take red, green, and near-infrared bands. The image was taken at an altitude of 760 meters above ground level, and this resulted in a resolution of 10 centimeters. Each image was taken in such a way that it created a 70% overlap on all sides, and the images were stitched together using Pix4D. The resulting orthomosaic image could be broken into the green image, red image, and the near-infrared image seen at the bottom of the slide. Completed images of the field were then imported into ArcMap 10.5, where the near-infrared image was used to create zones in the fields. The near-infrared image was used based off of research conducted by Andrew Robeson, who found that near-infrared pixel values correlated the best to yield in Australia. This is thought to be because of the fact that the near-infrared wavelength shows the greatest difference between healthy and stressed plants when compared to the green and red wavelengths. The near-infrared was subjected to unsupervised classification, and a color map was applied to aid in the creation of zones. The images at the bottom of the slide are an example of this. Red denotes a lower near-infrared pixel value, while green denotes a higher near-infrared pixel value. Zones were created based off of the near-infrared color map, the layout of the field, and the harvest method. The zones were created in such a way that a grower could easily break up the field and harvest the areas independently. This process resulted in a total of 18 zones in 2018 across the 3 fields, and 46 zones in 2019 across the 14 fields. Zones were harvested independently of each other to collect the following crop quality parameters. They were TSMK, SMK, SS, LSK, FM, and OK. Each zone also had yield recorded for it. And the 10 VIs shown here on the right were also created for each of the zones using the aerial images collected. The mean pixel value for each of the zones was recorded and was correlated to yield and each of the crop quality parameters. This table shows the results for all zones. Correlation coefficients shown in yellow are greater than 0.5, and this will be the same setup for all tables shown in the presentation. The correlation showed promising results for VIs versus crop quality parameters. When looking at the correlations between the crop quality parameters, we found that yield was highly correlated to TSMK, LSK, and FM, while TSMK was highly correlated to LSK, OK, and FM. Looking at how the VIs correlated to yield and crop quality parameters, there are many highly correlated parameters. Yield and LSK were both correlated the highest with the green ratio vegetation index. This is a ratio of the near-infrared and green bands, and this index has been shown to be sensitive to photosynthetic rates in vegetation, as green and red reflectance are strongly influenced by changes in leaf pigment. So this could be the reasoning behind its correlation to yield. TSMK and OK had the strongest correlations to the normalized red VI. This VI is the red band divided by the sum of all 3 bands. And similarly, SS was also correlated to the green normalized VI, which is the green band divided by the sum of all 3 bands. These normalized indices are used to standardize pixel values across the image. FM had the highest correlation with the difference VI. This index is the red band subtracted from the near-infrared band. This VI has been shown in research to distinguish between soil and vegetation. However, it does not account for the difference between reflectance and radiance caused by atmospheric effects or shadows. However, it is not evident how this reflects on foreign material in a grade sample. So looking at all of these VIs, these are the 4 VIs that we believe could be used to create a model to predict crop quality and yield in the future. However, we did not look at interactions between the VIs and parameters, so we decided to break out the data a little bit more. First, we wanted to look at the year-to-year difference. It is interesting to see that yield in 2018 had 6 VIs that were strongly correlated to yield, while there were none in 2019. One of the main differences between the years was Hurricane Michael in 2018. In 2018, the dryland fields received significantly more rainfall than dryland fields in 2019 did. This made us believe that VIs may be used to tell differences between well-irrigated crops better than dry stressed crops. Therefore, we looked at the 2019 results and separated out dryland versus irrigated. When you look at the graph, the tables, there are no correlations for yield. However, there are lots of highly correlated crop quality parameters for the other factors, and there's none in the dryland fields. This supports our previous theory. On the left is a near-infrared image of one of the fields used for this research in 2019. It shows the original color map that has been applied to it, and the zones are on the image as well. The middle image shows yield, while the image on the right shows TSMK. While looking at the individual fields used in this research, we noticed that the zone with the lowest near-infrared pixel values generally had the lowest yield in TSMK. We also noticed this for the other end of the spectrum with the highest yield in TSMK. This shows that this method could be used to identify problem areas of the field as well as the best areas of the field. But we need further research to identify the middle areas of the field. So in conclusion, across years, yield was correlated to TSMK, LSK, and FM, while yield and LSK had the strongest correlation with the green ratio vegetation index. TSMK and OK had the strongest correlation with the normalized red VI, while SS had the strongest correlation with the normalized green VI, and FM had the strongest correlation with the difference VI. Weather is a vital piece of data for understanding year-to-year differences, and that needs to be further looked at. And we found that irrigation can help to improve correlations between crop quality parameters and VIs. We also found that VIs can be used to identify the worst and best areas of a field, especially in prolonged weather events. And this can help to identify stressed areas which can directly affect crop quality. And this can relate to things such as aflatoxin and disease. Therefore, we decided to partially reject the hypothesis because we did find that crop quality parameters were strongly correlated to VIs. However, when breaking them out, we found discrepancies. For future research, we look to explore the interactions between the crop quality parameters and use VIs with the strongest correlations to crop quality parameters to create a model to predict overall crop quality. And we would like to integrate all management decisions into a web-based portal called the Peanut Health Network, which can be used to predict yield and crop quality at the field and farm level, and it can predict the risk of major stressors at all levels. With that, I'd like to thank my funding sources, Premium Peanut and the University of Georgia Crop and Soil Sciences Department, along with my major professor and my committee members, and the University of Georgia Peanut Agronomics team. Thank you, and I'll now take any questions.
Thank you for this presentation. And we have, starting off, your first question is from Dr. Dylan Wan. Do you think maturity may have played a role in the correlation between normalized RVI and TSMK? Okay, if I read that correctly.
The question is, do I think that maturity played into the normalized VIs and their crop quality parameters?
Yes.
I do think that maturity played into that. However, we did not collect that data for this part of the project.
And the second question is how do you see that perhaps crop consultants or others who are professionals might be able to use this kind of information as far as their own work and further the effort that you've begun?
The question is, how can crop consultants use this to further their own work? One of the ways that I believe this can be used is by looking at the problem areas of the field and identifying those. And so we're not putting as many resources into that if it cannot be brought up to the rest of the standard of the field. And that way we can divide that section out, and hopefully if we have a higher grade for the rest of the field, balance that out and get a higher premium for the grower.
Okay. All right, thank you. That's the time we have for questions, and thank you for your presentation.